All right. What did we cover last class? Yeah. What are these? Yeah, right. These are matrices such that this is always greater than 0. If this is satisfied, then this is positive definite. If it's greater than or equal to 0, pasty. Yes. Okay. And then, yeah. Okay. You have a matrix A. What is the definition of the Frobenius norm? Well, well, okay. So this is um, treating this like a vector. Treating what is the other type of norm used? So here we treat because a matrix A represents P. Let's say this is a P cross Q matrix. It represents a map from RQ to RP. Uh, the induced matrix norm tells us something about the gain map. All right. How is it defined? Is there only one induced matrix now, or are there many induced matrices? Yeah, many. Okay. Okay. The P. Okay. Okay. What does this mean? That means if you have vector y that is equal to x, the pth norm of y will always be, so this is equal to the pth norm of p. This will always be less than or equal to what? What is c? Now, how is this related to this? Okay, can I write it like this? Is that okay? Yeah. So the length of the so-called output vector will always be less than the length of the input vector multiplied by the pth norm. Okay. And then we looked at some examples, no? Not some examples. For these special norms, for these we know what the corresponding matrix norms are. What is it for this? This is only when it's square, right? Later on in the next module, we'll see that even if A is rectangle, you can define the second induced norm, and that will be simply the first singular value. This we'll discuss in the next class. Okay. Sorry. Ah, yes. Yeah. First term of what? What is AI? Did you guys think about why it is like this? You can think about why it is like in here. In the first law. So this is what we covered, right? This class will discuss an area of application where the idea of eigenvalue and eigenvectors and matrix norms actually come in handy. That is in the context of linear dynamic, right? Now we have system with some input u of t and output y of t. Um, I mean, you are probably familiar from your courses in signals and systems about when is this system with memory? Yeah. When does the system have memory? Sorry. No. When does it have memory? Right. If the output depends on the present and past inputs, you say it's memory. Well, by definition, the output can also depend on the future values of the input. But let's say we are only dealing with causal system. Okay? Then, if the output of your system depends on the present and past values of the input, then you say the system has memory. Okay, because the input is continuously changing here, right? And if the system's output depends on the past values of the input, that means the system is in some way storing information about the past values of the input here inside this box to produce an output y of t at any given instant in time. So we say if that is the case, then we say it's a system with memory. What about a system without memory? What can you say about the input-output relationship then? No, no, no. Linearity and memory they have no connection. Right. If the output only depends on the present value of the input, there is no memory inside. Whatever goes in gets processed and comes out immediately, and then it's forgotten. Right. Now, systems without memory are okay. For example, um, if you had a resistor and the input was, let's say, the voltage across the resistor, and the output was current, then you say the I equals V by R. Is this a system with or without memory? Without memory. Why? So, yeah, okay. Because the current value of the current through the resistor only depends on the potential difference across the resistor. Let's say the input was current here. It's with memory, is it? Why? So the current, okay, here, that means the output V is is what? Well, I'm not interested in the derivative of the output. I'm interested in the actual or the voltage across the capacitor. What is the voltage across the capacitor if the if the input and the output are related like this? Well, then you simply, right. That means here, this would go from, let's say this is a dummy variable L, the voltage at time t is simply the integral of whatever current was applied from the start of time, from minus infinity to current time. The integral of that will be the voltage that appears across the capacitor. That means in this case, the capacitor actually, uh, when you do an integration, it's kind of remembering the past by simply accumulating what was there before, right? So it does have so something like this has memory, right? And whenever you have a system with memory, then we say it's a dynamical system. If it does not have memory, then we say it's static. But for now, what we will do is we will simply treat any system, we'll call any general system as a dynamical system, except if it's system without memory, then it's just, let's assume it's just a special case of a dynamical system where there is no memory. Now, in general, the input-output relationship uh, uh, in physical systems like this are often related or relate to each other through, if you're talking about continuous time systems, through differential equations that relate the input with the output. For example, this. Okay. Here, the derivative of the output multiplied by C was equal to the input. So in general, you could have a situation like this where um, dt plus um, k1 of x dn minus 1 y dt n minus 1 a2 well, x of t. I'm simply dropping the t because it's easy. I don't want to write the dependence on t minus 2, so on and so forth. A n x, what? It's in general, the input-output relationship could have, so it might not be just your input f of fx, it could be some nonlinear function of your input. So if you have in a general system, then you might have a nonlinear differential equation that connects uh, the input to the output. Okay. Now, you say that a system H is linear. Let's say we want to restrict our discussions only to linear systems. You say H is linear. What is the condition for H to be linear? Yeah, right. So if it follows the, what is the superposition principle? Right. Now, if you have the system H, if I apply U1 of t and I get Y1 t, and if I apply U2 of t, and I get Y2 of t, if the system is linear, then if I apply alpha 1 U1 plus alpha 2 U2, I've dropped the t's. And if my output is simply alpha 1 Y1, alpha 2 Y2, for all possible U1 U2, and for all possible alpha 1 alpha 2, then you say the system is linear. Okay, that's simple. Okay, if you have a linear system, okay, then see these coefficients or these terms that you see in front of these derivative terms, these will not be functions of the input. These cannot be functions of input, of the input. Okay, we'll add one more condition. Or when is this time invariant? And what do we mean by time invariant? Right. If the system itself does not change over time, okay, then you say it's time invariant. And what is the mathematical condition for time invariance? So if I apply u of t and I get y of t. What is the condition for it to be time invariant? No, it does not. It does not have anything to do with scaling of the input, right? T minus what? Okay. What does this mean? That means if you had u of, let's say we applied this input u of t today and we observed some output y of t, and now if we apply the same input some other time in the future, or if we had applied it in the past, if the system produces the same time shifted output, for example, today the output for u of t was y of t. If I apply it tomorrow, if I apply u of t tomorrow, capital T tells me that I'm applying it tomorrow. The output that I get will be y of t, but appearing tomorrow. If I apply it 10 years back, the output that I get is y of t, but occurring 10 years before compared to the current time instant. So if this is satisfied, then you say it's time invariant, which essentially means the system itself does not change with time. Okay. And there is no relationship between linearity and time invariance. Okay. You can have a linear system that is time variant. You can have a nonlinear system that's time variant, and similarly linear time invariant system and nonlinear time invariant system. Okay. We will restrict our attention only to these. Okay, because this is a reasonable assumption for most systems. And out of all these, the linear time invariant systems are the simplest to study. And since they are quite applicable in practice, it makes sense to work with these, or at least make this assumption about your system. Okay. If that is the case, right, if you are in fact dealing with a linear time invariant system, let's say we are still only concentrating on continuous time systems, then it turns out that the input output relationship is described by linear constant coefficient differential equations, okay, of this form. Let's say you have a system u of t, y of t. Then in general, a system like this is described by a differential equation like this. Okay. You could have other fancy versions as well, where you could, on this side, you could have derivatives of your input. We'll restrict our attention to this. Okay. Then the input output relationship of such as if for of a linear time invariant system, continuous time system, can be described by a differential equation like this. And this a1 to an are constants. Okay. Now, if you have a if you have a linear time variant system, all that changes in this is your these would be functions of time. Instead of this being a constant value, it will simply be a1 of t, a2 of t, and so on and so forth. Okay. If they're all constant values, numbers, then what you're dealing with is a linear time invariant system. Okay. Now, let's take a simple example. And n, what is n here? What does n stand for? N is an integer, positive integer. Yeah, the order of the system. Okay. Let's say we're dealing with a, first order system. Okay. Where okay. Okay. And for simplicity, yeah, let's say we have a system like this. Okay. How would you compute the output of a system like this? Let's say H was described by this. In fact, to make it simpler, we will even remove the A1. Say I had a system where the derivative of the output was a function of was equal to the input. How would we compute the output in this case? What would be, okay, you integrate dl, and what will be the limits of your integration? Okay. See, what this says is the rate at which the output changes depends on the input, right? So if I know the input, uh, all my input is doing is determining how much my output changes by. Okay. And if you simply add all the changes and the change is equal to the input, then you get the value at time t. And when I say add all the changes in the output, starting from time t equals minus infinity, and if you add all those changes from the start to the current time t, then that is your output. Okay. And this is a system with memory because you to compute the current output, you need to know the value of the input at time t, time slightly before t, and slightly before that. In fact, for a simple system like this, if you want to calculate the output, right, you need to know the entire time history of your input. If you don't have it, or at least the way it's written down here, if you don't have the entire time history of your input, you cannot compute the output. Okay. I mean, that is a problem. Okay. But here, because we might, for example, let's say this is a system, we might get interested in the system maybe only now, right? Before that, we didn't care what was going on with the system, right? It was getting some input and it was producing some output. But maybe at this time instant, we want to manipulate the input and then compute the output. If the input-output relationship is given by this, then this means that there is no way for us to compute the output at any given time t from this point on, because we have no idea what the input was. Okay, but if you look at this expression, right, you remember from your integral calculus, if you integrate function f of x dx from a to b, the integration can be split, right? If you choose a point between a and b, a point in between a and b, then you can write it as integral from a to c and c to a, right? C to b, sorry, yeah, right? So using that idea, let's say we got interested in the systems at some time t naught, okay? Then we can write it like this: dl and t naught, right? That's a valid way of writing it. What is this? Well, yeah, exactly. So this is simply y of t naught. That means my output at y of t is simply t dl plus. So what this tells me is, in fact, I don't need all the past history of my input. All I need, if I am interested in, if I get interested in the system at time t naught, as long as I know what the input was from time t naught, and I know what the output of the system was at time t naught when I was interested in the system, that is all I need. If I have y of t naught and the input that went into the system from time t naught, then I can compute my output for any time greater than t naught. Okay. That is good news, because now all we have to do, if I'm interested in the system now, I observe what the current output is, and then if I have control, if I know what the input is from the time at which I got interested in the system, then I can now at least compute the output for any arbitrary input that I am interested in giving from a time t naught. Okay? And that means this value here is essentially the memory in the system that contains all the relevant information uh, for the input output relationship of the system, and it contains all the necessary information that is useful for determining the output starting from the time t equals minus infinity until that point t naught. So this contains all the information that you need. So if you want to compute the output of the system starting from this time t naught, you only need this value and your input, and any such variable of the system that is sufficient. If you know the value of that variable and the input of the system, using those two, if you can compute the output of the system for any arbitrary input, then this variable that you have is called the state of a system. Okay? That's the definition of the state. Any variable associated with your system, such that if you know the value of the state and the input, then you can compute the output of the system for any time that point onwards. Okay? Provided you know the input. And state is essentially what holds is the memory of the past inputs before this time t naught. So for a system like this, right, the the variable y of t was the state of the system. What about something like this? So here there was only one state. What about something like this? How many states do you think this? So this, it turns out, will have two states. And this is again a linear time invariant system. Two possible states here are simply y and dy by dt. If you know these two at some time, for example, now if we got interested in the system at time t naught, and you know y of t naught, and you know dy by dt at t naught, and you know the input y of t for all t greater than or equal to t naught, then with this three pieces of information, you can compute y of t for any time greater than t naught. Okay, that means now for a general LTI system like this, in fact, see, this idea of state applies for nonlinear systems as well, nonlinear time variant systems as well. We are simply only talking about uh, linear time invariant systems. So if you have a general system like this, how many states would the system have? So this would have n states. And what might those states be, or one possible set of states for the system? Yeah. So the states would be y of t dt d square y by dt square until en minus 1. When you were studying this in mathematics, you might have just called these the initial states, or no, initial conditions, sorry, right? So whenever you have a differential equation that you're solving, whatever initial condition that you need, those are potentially the states of the system. Okay, and they are not unique. The states of a system are not unique. You can have infinitely many possible states. Okay, if you have a differential equation like this is one valid possible set of states for this system. Okay, and as I said before, states are associated with memory in the system. And in terms of, if you're dealing with physical systems, states are simply variables associated with energy storage elements in the system. Let's look at a couple of examples. So this is u of t, your input. This is your y. What is the input-output relationship in this case? And you can write down Kirchhoff's what loop law or whatever that is called. No, I want it in time domain. I want a differential equation connecting u of t and v of t. Assume that there is a current I that is flowing through this. Okay, I'll write it. So if you write the loop equation, let's see the voltage across this is VR. So VR plus Y equals U. VR is simply R times I. Y plus U. Now, Y is simply the voltage across the capacitor. What is the relationship between, how do you find the voltage across the capacitor? No, the voltage in the across the capacitor. What does it depend on? Sure. Integration of I, or if you know the charge on the capacitor, what is the relationship between the voltage and the charge on the capacitor? C equals U. What is I? Well, I is simply the current that is flowing through the circuit. And if Q is the charge on the capacitor, I would simply be the rate at which the charge on the capacitor is changing because the current is flowing through only through this loop. Whatever current passes through the capacitor, passes through the capacitor. So through the resistor, passes through the capacitor. If a current flows through the capacitor, that means the charge on the capacitor is changing. That means I must be equal to Qy dt. Okay. Now, if you look at this, right? I mean, we started with the problem saying, well, we are interested in the output, which is voltage across the capacitor, and this is the input. But we've come up with an expression that does not seem to have y of t. Okay, but it does. What we have seems to be in terms of this variable q, and it turns out when you have an RC circuit, uh, q charge q on the capacitor is a state of the system. Okay. So what you have here is not the input-output relationship, but an expression that tells you how the state of the system changes depending on the input that you apply. Okay. And remember, earlier I said states are associated with memory, and these are memory is essentially uh, uh, relates to the energy that is stored in the system. So states are states that you have are essentially variables associated with energy storage elements. What is the energy storage element here? Capacitor is an energy storage element, and it stores what? Potential energy through the electric field across its plates, right? And the amount of energy that is stored is determined by the variable Q. So that's the state associated with the energy storage element in the circuit. Right? So what we ended up having here is not really an input-output relationship, but something that tells you how the state of the system changes with the input. Right? Now, if you can solve for Q, it's easy to find out the output in terms of Q. What is the output in terms of what is y of t now? In terms of Q, simply this. Right? So if you can solve for the state, then the output is easy to find. Right? So it turns out, see, whenever you have an nth order differential equation like this, there is another way to express a system like this, which in a way is a little, at least in terms of, it looks a little simpler. Another way of representing a linear dynamical system like this, and it also reveals a little bit more than a, a nth order differential equation like this. Now there, or in general, whenever you have a system like this, it turns out a linear dynamical system, instead of just writing the input-output relationship like this, we take the input, okay, we ask, how does it affect the states? So we have what is called a state equation that tells us how the states of the system are affected. And then once you know the state of the system, from this, it goes to output equation, and then you get y of t. Okay? It might seem like a roundabout way of just talking about that, but there is something to be gained by expressing this input-output relationship in this form. And if we are talking about a linear time invariant system, it turns out that you can express an nth order differential equation like this as a first order matrix differential equation. Okay, I'll simply write it down, and then I'll explain what these are. I've dropped the dependence on time just to make it simpler. And remember, if you have a vector x, right, these could be simply numbers. But if the vector x is a function of time, then each of these elements is a function of time. Okay. So now all of these are function of time. And we've not seen this before. X dot is simply first derivative of this vector. The definition for a derivative of vector is very simple. If you say that you're taking the derivative of this vector, all you're doing is you're taking the derivative of each of these individual terms with respect to time. That's all. Okay. So this is what is called the state space representation of a linear time invariant system. Okay. And this is called, the first equation is called the state equation. It tells you how the state of the system changes uh, with respect to the input and the current value of the state. And the second equation is the output equation that simply tells you how the output that you're interested in is related to the state of the system and related to the input of the system. And these are matrices of the appropriate size. Okay. I'll just before we continue, let's say there are n states in the system. Okay, and let's say there are p inputs. We've only talked about single input system so far, but we'll come to a more general discussion a little later. Say there are p inputs to the system, and let's say there are q outputs that you're interested in. Okay. Now tell me what will be the sizes of the four matrices A, B, D. What will be the size of A? Well, if X is of size, X is from Rn, where will X dot be from? Well, Rn, because it's simply it's still n, it's got n elements. So X dot is from Rn. So what is the size of A? N cross n. Okay. What about B? Are you sure? Yeah, n cross P. Okay. What about C? There are Q outputs. Yeah. And D? Yeah, that's all. Okay. I forget what the name of this matrix is. There is a nice name. I think this is called it's in the slides. You can refer. It's got a nice name. A's got a nice name. System matrix. Yes, that's right. This is called the system matrix because A is something that fits inside the box. I mean, in fact, all of them sit inside the box, but A is called the system matrix because even if you don't apply any input to the system, right, there is something that is going on inside that is entirely determined by the characteristics of the system itself. That's why it's called the system matrix. B is called the originally input matrix. C, I think, is called the output matrix. This is called the feed forward matrix because this is as if here. What does D do? D relates the input directly to the output, right? So it's as if D is this. It does not go through the state evolution, but in fact directly affects the output. So it's as if it's fed through directly. So it's called the feed forward matrix. And in fact, D is the component which has no memory because see, this is U of t, this is Y of t. D relates them directly. So any memory less component in this whole thing, in terms of the input output relationship, is contributed by D. Okay. Now, let's try and express this RC circuit. We know what the input is. We know that the system has one state. And we know what the output we are interested in. What is the output that we are interested in? How do we express? Now, what will be, you can tell me the sizes of A, B, C, and D. There is one input, one output, one state. All of these will simply be 1 cross 1 matrices. Okay? Well, yes, okay. So tell me the state equation for this system, which should be x dot equals x plus bu. That's essentially this. If q is the state, right? So let me write it like this. It's got only one state. It's a scalar, but I'll use the matrix notation, vector and matrix notation anyway. Right? That means now x dot is simply equal to q dot. Well, I know what is q dot from here. Q dot, this is q dot. So this is simply equal to, if I move this here, then this will simply be minus q by rc plus u. Okay. Now I can split this in that form. I can write it as minus 1 by RC multiplied by Q. Well, this is U, but I can write it like this. Sorry, yes, yeah, by R. Okay, that is my state evolution equation. That's how my state evolves over time. What about my output now? Well, my output is this. It's simply 1 by C times my state. So that will simply be C multiplied by Q plus, yes, there is no direct feed through because it does not depend on U. So this will be, okay. So for this system, what are your four matrices? A is simply minus 1 by RC. B is 1 by R. C is 1 by C. And D is simply 0. Okay. All right. I hope that gives you some idea about this. Let's do something that's got two states so that we also see a case where A, B, C, D are matrices. Simply add. Now tell me, do the same thing and then tell me what you get. So you simply do VR plus VL plus VG will be equal to, if I is the current that's flowing through the circuit, then you have I times R. You do the same thing here. What about this? Hold on. What is the voltage across the inductor? What is the relationship between the current flowing through the inductor and the voltage across the inductor? Yes. What is okay? What is voltage? How is voltage related to the current in differential form? Yes, this is L into. Well, if there is a constant current flowing through the inductor, there is no voltage across the inductor. If it's got zero, assuming it's got zero resistance, right? Okay. Well, now there is a Q here, and we can now express both of these in terms of Q. So if you do that, then you get R times dq by dt plus, now here this will be second derivative of Q square plus Q by C U. How many states does this system have now? Okay. I mean, without worrying about the actual physical system, what are two possible states for if you have a differential equation like this? Well, Q and in earlier, again, I said the states are variables associated with uh, energy storage elements. What are the two energy storage elements here? Capacitor we already saw. The variable associated with this is Q. What is the corresponding energy? Oh, sorry. What is the variable associated with L? Not change in current, no? I mean, what form is the energy stored in an inductor? No, not current. Here it's the electric field because you've separated charge. And what determines the magnetic field? There's the current, no? The amount of current, no, not the change in current. Even if I have constant current flowing through my inductor, there is magnetic field that is generated. No, if I have a constant current that's flowing through, I do have a magnetic field that's set up. No, so in fact, just the current that is flowing through the inductor determines how much energy is stored in the inductor, right? In fact, we see that's nothing but this. Okay, so there are two states here. Now, tell me what is the state evolution equation now? State equation. I'll remove this. Then you can tell me what the state equation is. What are the states now? What will be the states? It'll be it'll be a 2 cross 1 vector now. And what are the two states? Well, just these two. Let's say we choose to write it like this. Those are the two states. Okay. Now, what about how do I find x dot? X dot is simply q dot, q double dot, derivative of this. Well, so now q dot is simply q dot. Q dot equals q dot. What is q double dot from here? Okay, what is it? Minus 1 by RC minus, so not 1 by RC. 1 by what? Okay, tell me whatever expression you get. There'll be a plus u here, some u, probably u by L. Okay, sorry, q by LC there, by L. Okay, now how do we write this in this form? Well, here it only depends on this q dot. Here there are two terms, so we can split this out. Can we write it like this? Now we need to express it like this. We need to come up with A and B. This is equal to q dot, q double dot. That is your x dot. What will this? Sorry. Hey, hold on. Here, the first equation is about q dot, right? What will this be? Yes, 0, 1. No, hold on. If this is 0, 0, then you're saying q double dot does not depend on any of my states. Right. So it will be minus. That's all. What about here? What will be the shape of or size of B? No, what is the size of B? N cross P. P is 1. Is it 1 cross 2? And 0 because there is no contribution. See? See, in fact, now in general, if I asked you what is the ijth element of the matrix A mean, you should be able to tell me what that means. It tells you how the ith state changes with respect to time, or it tells you the derivative of the ith state and the influence of the jth state on the derivative of the ith state. And similarly, some bij term. Okay. Now, this is all internal. Okay. States stay within the system. Okay. This simply tells you how things inside this RC circuit evolve depending on the function, depending on what input you apply. Okay. Now, let's say here I'm measuring two things. I'm measuring this, and I'm measuring the current let's say there are two things that I'm interested in: voltage across the capacitor and the current through the circuit. So my y has two variables, right? So, okay, let me write it down. Now, y1 is Vc, y2 is I. Now we need to get expressions for these in terms of the states and in terms of the input u of t. How is y1 related to the state or the input? It's simply q by c, does not depend on the input. What about I? Well, I is just q dot, the second state. That's it. Okay, so that means now my output that I'm interested in, y1, y2, what is my C matrix now? So that depends on q dot, and u. What is the size of q? 2 cross 2. Okay. All right. What will be the elements of C now? Zero, is it? Zero. That's all. And here, there are two outputs, so it has to be 2 cross 1. What if I had a third measurement? In fact, I had a third measurement, which is simply, um, I'm also measuring the voltage across the resistance. And I can measure whatever I want from this, right? Well, this is simply R times Q dot. So how will this change now? So this will now become Y3. What will be the shape of this? It will be 3 cross 2. And what will be the third row? So it will simply be 0 R. See, I do something even more crazy. I take these two voltages and then I add it through a adder, okay, uh, such that, so I take this voltage, multiplied by some I amplify it by some factor alpha 2, amplify this by some factor alpha, and then I add it, and this is my y4. Don't ask me why I'm doing this. My application requires me to do this. Okay? So now y4 is alpha 1 times Vc plus alpha 2 times VR. Now what is, so this will become y4 now. This will be a 4 cross, see, I missed one thing. Earlier this was 3 cross 1, now it will be 4 cross 1. What do I get here? Y4 is simply alpha 1 times Vc plus alpha 2 times VR. Yeah, alpha 1 by C R alpha. That's it. Okay. See, now the nice thing about this framework, right? This is simply the physics of the system, okay? And how uh, uh, things internally to the system change as you apply the input. And what we end up measuring from the system, that could vary, right? So when I started with the circuit, I was only interested in this, okay? Later on, I went and said, oh, I want to measure the current. And then I said voltage across the resistor and all that. None of these, the measurements that I make from the outside, actually affect how this behaves, right? So they in no way affected my first equation, the state evolution equation. Depending on what you wanted to measure, all that changed was your measurement equation. Okay. Now, in fact, the nice thing about this is, let's say you're measuring the voltage across, let's say, the capacitor, but by using multiple sensors. Okay. Each one, let's say, has a different sensitivity, different noise characteristics. all of that can simply be put in the C matrix. So let's say I have two voltmeters, both of them measuring the voltage across the capacitor. Let's say one is measuring it in millivolts, other one is measuring it in volts. Then I would simply have my C matrix to be 1 by C into 1000 because I'm measuring in millivolts. The other one would simply be 1 by C. So you can put all that in. Okay. And in fact, an extension of this, if you want to also account for noise in your system, you can then add the noise in your measurements. And in fact, if each of your sensors has a different amount of noise, you can account for all of that using this model. That's a nice, that is what you gain by separate, instead of relating u to an nth order differential equation relating to some output y that you're interested in. If you do it this way, then you get a more general framework for dealing with stuff. Now, in fact, instead of having this, if I had a more complicated circuit with another voltage source here, then this would be u2, this will be u1. Then, of course, see now the state equation also will change because now there are two input. The internal evolution of the internal system has changed, right? Now this will be different, and so you have a different state evolution equation, and depending on what you measure, you have a different. All right. So that's what. So uh, so linear algebra comes uh, in very handy when we're dealing with linear time invariant systems like this. In fact, the it you can express all this also in terms in the general case. If you're dealing with a nonlinear system, then you'd have something like this. Okay. This evolution, the rate of change of the state of your system will depend on your input and your state through some nonlinear function f, and the measurement that you're making again could be some nonlinear function of your state and your input. Okay. A special case of this is here. Okay. And if you are dealing with multi-input, multi-output systems, like here, like in this case, a nonlinear multi-input, multi-output system, some of the ideas that we've discussed in linear algebra are still very much useful here in analyzing a system like this or developing controllers for changing the behavior of the system and all that. Okay, quickly move on to. I'm only going to be talking about continuous time systems. You can look at the slides to learn about discrete time. Discrete time is relatively easier. Now, so if we are interested in, let's say, now, so here, what I have is how does my state evolve and how does my output depend on my state and my input. We can come up with an expression for how the state evolves given an input or given given some initial state. And using that, you can then also compute what will be the output of my system given an initial state and given my input. We will look at what is called the zero input response. Simply, if you have a system which starts off from with some initial condition, how do the states of the system evolve over time if you had a linear time invariant system like this? Right? For example, let's take the simplest case, the where the number of states is one. That would be a case like this, where dx by dt is simply equal to some a times x. Okay, b is 0 or b is not 0, u is 0. Okay, let's say x of t is a scalar. Okay, what is the solution to an equation like this? This we are I mean, this we've done, no? Do you remember? Where the rate of change of a variable is proportional to the variable itself. Yeah, what is it? X of t will simply be e power at into x of 0. Okay, where x of 0 is it's the initial value of the state of the system, and for us the initial value is at time t equals 0. This we've seen. Okay? But now what we're dealing with uh, is not a scalar expression like this, but a vector relating to a vector through a matrix, right? So what we have is this. Okay, and it turns out, again, another beautiful thing about the subject, the zero input response of a system. Well, I should have defined this. When I say zero input response, I'm simply talking about the input to the system is 0, and the behavior of the system is entirely driven by some non-zero value for your state at some time t equals 0, assuming t equals 0 is the time from which we are interested in the system. Okay? If that is the case, then if you have a system with a single state, then the evolution of the state is given by this. So your state would, the value of the state at time t equals 0 will exponentially explode or exponentially decay depending on the value of a, if the input or the state evolution expression is like this, assuming 0 input. It turns out if you have a system like this and the initial state that you're interested in is uh, 0, x of 0, the state at any given time t is simply e times ea. Okay, exponential raised to a matrix. Okay, maybe at first maybe this looks a bit strange, but again, I mean, this is true, and you should see. I mean, you see the analogy between these two, and it's kind of beautiful, right? If you have a scalar system, it's e power at. Instead of just having one state relating one state and its state evolution equation, if you have multiple states related through for a linear time invariant system, the evolution of the individual states is essentially given by exponential of a matrix multiplied by the initial value of the state. Okay, now we have to define what this is. Okay, okay, so e power ta. Well, what is e power 8 in this case? What is the definition of the exponential? Do you remember the infinite series for e power x? Yep. Right. By 3 factorial and so on and so forth. It's exactly this. The definition for a metric exponential is essentially the same. If you say e power, I'm going to drop t for now. If you have e power a, e raised to a matrix, it's simply, the definition is simply this: I a plus a square by 2 factorial, a cube by 3 factorial. Okay. So the exponential of a matrix is essentially a infinite time series where the individual terms are powers of the matrix itself. Okay. See, now you could ask, well, wouldn't this just simply explode to infinity? It turns out it does not. Okay. Now, if you're talking about then e power t a, t is a scalar, then this will be e power t, this will be a square t square, a square t cube, and so on and so forth. And see, in the case of scalar, you need all the infinite terms to compute the exact value of e power x. It turns out, in terms of, in the case of a matrix, you don't have to compute all the infinite powers of a matrix. You only need uh, a square, and a n minus 1. Can you read this? Yeah. Or maybe this. Okay, you don't need anything beyond this. Okay, again, I'll not go into the details of this. You can refer to the slides. This is because of what is called the okay, you can refer to this, why it is so. So if you just with this, you can compute e power ta. Okay. In fact, it turns out e power ta. Now, A is a square matrix, right? Let's assume A is diagonalizable. And what does it mean when I say A is diagonalizable? Matrix, okay. That means there is a similar matrix lambda, which is a diagonal matrix. What goes on here and here? Let's call it V. Let's say the eigenvectors are V. Is that okay? Is that okay? Is it V inverse V or V? No. Are you saying that just because I asked you, or are you sure? Okay. Well, this is in the matrix A looks like a diagonal matrix in the eigenvector basis. V inverse takes stuff from the standard basis to the eigenvector basis. Okay. If you have things like this, you remember, I don't know if you remember, what is A square? If you can express, if you can diagonalize A, what is A square? A square will simply be V inverse, V inverse. This disappears. So it turns out if you have A power K, this is simply V lambda power K V inverse. Okay. Whenever A is diagonalizable, higher powers of A can simply be obtained uh, by an expression like this. Okay. So it turns out because the matrix exponential is a sum of higher powers of A, e power ta is simply V e power t lambda inverse. Okay. E power t lambda has a simple definition. Okay. What is lambda? The matrix lambda 1, lambda 2, lambda n. These are the eigenvalues of your matrix A. E power p lambda has a nice simple definition. We don't have to, well, we are talking about a matrix exponential. That means you'll have to compute it from the higher powers of that matrix t lambda. But it turns out if you do the computation, it'll simply come out to be okay. That means the matrix that you have in the center here looks like this. There are zeros here. Okay. Now, if you remember earlier when we were discussing eigenvalues and eigen vectors, I said the eigenvalues of a matrix uh, in the context of linear time invariant systems relate to the poles of the system. Okay. So now you see how it might be related to the poles of the system. Now, for this system, the pole is at A. Okay. If you have a general system like this, turns out the poles are at lambda 1, lambda 2 to lambda n. And the real values of the poles, lambda 1, these are in general complex numbers. The real values of the poles, lambda 1, lambda 2 to lambda n, will determine whether or not these exponential terms grow, decay, or stay constant. Okay? If the real value is 0, then the magnitude of e power lambda will be 1. If the real value is negative, then it will exponentially decay. If the real values of these lambdas is positive, then it will grow. Right? I mean, these are fixed numbers, right? If you have an exponentially growing term here, then the response that you get for some initial condition will have a growing state. Well, depends on the exact sign of the real values of lambda 1 to lambda n. Let's say lambda 1 had a negative real value, then the well the very first, well, it's complicated, but yeah. Let's say this was negative and this was positive, and the few other values were negative, some was zero. Then these numbers in general, some of them might grow, some of them might decay, some of them might stay constant. Okay, and that is where eigenvalues and eigenvectors are useful in the context of linear dynamical systems. So we'll stop here. We'll quickly talk about stability tomorrow, and then we'll discuss any questions you guys have till matrix inverse, so that you are prepared for your midsem. Please come prepared with questions that are not clear, okay? Because that's your last chance to discuss before the midsem. Are there any questions for today? Okay, all right. Then we stop it.